10, part A says fill in the blank. If a sub n approaches L as n approaches infinity, then a sub n plus 1 will approach what as n approaches infinity? And there's a hint here, it says as well. All right, so you see the sequence in blue converging to the number L, and let's just recall what that says exactly. It says that if you give me any window around this number L, so say this window here illustrated in green, then the fact that the sequence converges to L says that there's some index such that all of the terms of the sequence past that index will fall within this window. Okay, so put another way, we can make the terms of the sequence as close to the number L by just moving far enough out in the sequence. Okay, so now if a sub n is within this window of L, okay, then a sub n plus 1, which is just the term that immediately follows a sub n, it will also be within that window. And so we conclude that if a sub n approaches L, then a sub n plus 1 will approach L as well. Okay, so now for part B, it says use the result from part A to compute the limit of each sequence described below. You may assume that each sequence converges. And look at the first example here. This is what we call a recurrence relation, right? So we're given this initial term a1, which is -1, and then we're given this recipe to generate subsequent terms. So in this case, to get from a sub n to a sub n plus 1, we compute this quantity a sub n plus 6 divided by a sub n plus 2. So here I've gone ahead and just computed the first 4 terms of the sequence just to get a feel for what it looks like. So a sub 1 is -1. To get a2, well, this is going to be a1 plus 6 divided by a1 plus 2. So then I just plug -1 in for a1, and then that all simplifies to 5. To compute a3, well, plug 5 in for a2, and that's going to give you 11/7. For a4, likewise, we wind up getting 53/25, so on and so forth. So here's the first 4 terms of the sequence, and our job is to compute the limit of this sequence, and we're assuming that the sequence does converge, okay? And so I'm going to call the limit of the sequence L, okay? So L is the limit as n approaches infinity of a sub n, and now from part A, since a sub n is approaching this number L, we know that a sub n plus 1 approaches L as well. And so now the idea is take this recurrence relation and take the limit of both sides. Okay, so I'm going to do that right here. Okay, I'm taking the limit of the left side as n approaches infinity and of the right side. And by what we just discussed in part A, okay, a sub n plus 1, it's going to approach L, and a sub n, which shows up on the right side here and here, it's approaching L. And so I get this algebraic equation, L from the left is equal to L plus 6 all divided by L plus 2. All right, so now do a little rearranging, and we wind up getting this nice quadratic equation. And this quadratic expression on the left happens to factor, which is great, and we get these 2 solutions. L is -3 and 2. Now, a sequence cannot converge to 2 different limits, right? So one of these values is valid for us and another is not, okay? So which one is valid? Well, notice here, right, aside from this very first term, all the subsequent terms of the sequence are going to be positive. If you imagine plugging in a positive number into this expression, which again, we start with a positive value in the second term, okay, this resulting expression will always be positive. So what we conclude there is that the limit must be non-negative because, well, again, all the terms of the sequence are non-negative, at least starting with the second term on, okay? So we can disregard -3, and that implies then this sequence will converge to a value of 2. Okay, so that's part 1 there. Let's look at the next example. All right, so with part 2, it's kind of an interesting sequence. We have this nesting of radicals, right? So we start with root 2, then we have the root of 2 plus the root of 2. Then we have the root of 2 plus, well, the root of 2 plus the root of 2, so on and so forth. Okay, so here is the key idea, right? We're going to approach this just like we did the first example and observe the following pattern, right? So here I have this first root 2. And then what do I do to get the second term? Well, I'm going to take the root of 2 plus the previous term, which is that root 2. How do I get to this next term? Well, I'm doing the root of 2 plus, well, the previous term, right? That thing in purple. So on and so forth. So in other words, to get from a sub n to the next term, a sub n plus 1, the rule is take the root of 2 plus that a sub n term. So this gives us a recurrence relation. And so just like in the last example, go ahead and take the limit of both sides, and we'll call that limit of a sub n, which again we're allowed to assume does exist, we'll call it L. So on the left, okay, this a sub n plus 1 is going to approach L, and on the right we're going to get the root of 2 plus the limit of a sub n, which again is just L. So now this just gives us an algebraic equation. Square both sides, move everything to the left. This again is a nice quadratic expression that factors, and we get these two solutions, 2 and -1. Now, each one of these terms is non-negative, so it doesn't make sense for the limit of the sequence to be a negative number. So that means, just like in the last example, okay, since the terms are all non-negative for n greater than or equal to 1, the limit must be non-negative, and so this sequence also converges to 2. And by the way, if you want to play around with this with the calculator, you can start with the square root of 2, and then you're just going to do plus square root of 2, plus, and then you just keep doing this, and you can see right now it does 3 iterations of about 1.96. Well, that's reasonably close to 2. 1.99, 1.997, and if you just keep going out, you just get closer and closer to the limiting value, which is 2. All right, cool. Last one here, so make a little space. All right, so we got the sequence 1, then 1 plus 1 over 1, then 1 plus 1 over 1 plus 1 over 1, okay, so on and so forth. Okay, so just like the last example, look for a recurrence relation. Okay, so notice here, the starting 1 in green shows up in the second term right there. This is 1 plus 1 over the previous term. Then the second term here, which I've underlined in blue, it shows up in the third term right here. And again, I'm doing 1 plus 1 over the previous term to get this third term. How do we get the fourth term? Well, 1 plus 1 over the third term. Okay, so on and so forth. So here's the general recurrence relation. A sub n plus 1 is equal to 1 plus 1 over a sub n. Okay, take limits of both sides. That's going to give us this algebraic equation. L is equal to 1 plus 1 over L. Okay, clear fractions, move everything to one side. We get L squared minus L minus 1 is 0. And I can solve this. This quadratic expression doesn't factor, but I can solve it using the quadratic formula, and it's equal to 1 plus or minus the square root of 5 all over 2. Okay, so again, two solutions. However, one of these solutions is positive and one of them is negative, just like we've seen before. Now, if I use the negative sign, this gives me a negative value for the limit, which doesn't make sense, because again, all of these terms are certainly non-negative. And so our conclusion here is that the limit of this sequence is this number 1 plus the square root of 5 all over 2, which is approximately 1.618. Okay, this is what's known as the golden ratio. Okay, and by repeating this process, 1 plus, 1 over 1 plus, 1 over 1 plus, blah, 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 this is what's known as a continued fraction representation of the number, in this case, it's called the golden ratio. Okay, so you might have heard of the golden ratio. Here it is, more digits of it. You do a quick Google search of the golden ratio, you're going to see, right, a whole bunch of Da Vinci Code looking kind of stuff. And interesting number. Check it out if you're interested. This is certainly an interesting way to generate the golden ratio. But in any event, that's going to do it for this problem. I will see you in the next video.